Hey there, it's Modern Retro Tech, and today we continue with Advent of Code. I plan to do days 7 and 8. I haven't read the solutions yet, but tasks yet, but I have seen some memes about bags and I guess about recursion. So I kind of know what the first part of the day 7 task will be, but let's try to actually read it and solve it. And yeah, of course, we will be doing it still with Rust. Handy haversacks. You land at the regional airport in the time for your next flight. In fact, it looks like you'll even have time to grab some food. All flights are currently delayed due to issues in luggage processing. Due to recent aviation regulations, many rules your puzzle input are being enforced about bags and their contents. Bags must be color-coded and must contain specific quantities of other color-coded bags. Apparently, nobody responsible for these regulations considered how long they would take to enforce. For example, consider the following rules. Light red bags contain 1 bright white bag, 2 muted yellow bags. Dark orange bags contain 3 bright white bags, 4 muted yellow bags. Bright white bag contains 1 shiny gold bag. Muted yellow bags contain 2 shiny gold bags, 9 faded blue bags, shiny gold bags, yada yada yada. Faded blue bags contain no other bags. Dotted black bags contain no other bags. These rules specify the required contents for 9 bag types. In this example, every faded blue bag is empty. Every vibrant plum bag contains 11 bags, 5 faded blue and 6 dotted black, and so on. You have a shiny gold bag. If you wanted to carry it in at least one other bag, how many different bags color would be valid for the outermost bag? Oh, okay. Okay, so faded blue bag empty. Vibrant plum bag contains 11 bags. 5 faded blue bags, 6 dotted black bags. Dotted black is empty, faded blue is empty. Okay, makes sense. You have a shiny gold bag. Contains 1 dark olive bag, 2 vibrant plum bags. If you wanted to carry it in at least one other bag, how many different bag colors would be valid for the outermost bag? In other words, how many colors can eventually contain at least 1 shiny gold bag? In the above rules, the following options would be available to you. A bright white bag, which can hold your shiny gold bag directly. So bright white will contain 1 shiny gold bag. It's always and, so you have like some color bag contains n of another color bags and m of yet another, or like no other bags, or more, I guess. A muted yellow bag, which can hold your shiny gold bag directly, plus some other bags. A dark orange bag, which can hold bright white and muted yellow bags, either of which could then hold your shiny gold bag. A light red bag, which can hold bright white and muted yellow bags, either of which could then hold your shiny gold bag. So in this example, the number of bag colors that can eventually contain at least 1 shiny gold bag is 4. How many bag colors can eventually contain at least 1 shiny gold bag? The list of rules is quite long. Make sure you get all of it. Okay. That sounds interesting. Sounds like some graph stuff, but typically in Advent, that's a lot of rules. Typically in Advent of Code, if you have something that looks like graph algorithms, you often can solve it a bit simpler. We will need to see. But first, let's start with the typical boilerplate, I guess. So, oops. So it ends with striped line bags. Okay. Also, let's already create sample 7 example for these rules so we can test our parsing a bit easier. So yeah, I need to add some kind of generator for this stuff, so I don't need to write it every time. But I guess that's it. Let's start with our parser, and I can switch to my Zen mode again. So we need to parse this stuff. I guess we will have at first a dictionary for each bag and like other bags. So let's model the structure we want to have. Bag. How do room? No, containment. Gosh. Color will be just string, I guess. And count will be size, just for simplicity. Now, that thing, we probably want to debug it. And we will definitely need equality, partial equality, ordering, blah, blah, blah. Actually, ordering, I guess we don't need, but I already know that we probably want to do some hash map stuff here. So we also will need to have hash. This is containment, and then rules will be which will be a hash map from actually, let's do it like that. We can do color, which will be string. So this is just a alias. We don't need to define anything additionally for it. It will be from color to contained to vector of contained. Oh, we don't need hash here. We just need debug. And then we can do parse, which will be take input, take reference to string, we return rules. So how do we parse this stuff? Contain one bright white bag, two muted yellow bags. Bags contain. So it always bags contain, I guess. Yeah. First have color, space, bags contain, space, either no other bags or a list of things. So I guess we won't do the regexes this time because I think that is easier to parse actually this just normal split stuff. So put split. I wonder why sometimes it shows stuff here, split, because then it's not visible at all. Yes, split ASCII white space. Actually, no. We only need to split on new lines. So, and first we also need to do trim end. That will be lines. Let's make a mutable hash map. And then we can do, so for each line of our input, we can split on back's contain. Space, actually. And then we can match it. And again, using my new favorite feature of subslice patterns, where we can say color rules. For now, I'll just do that. Gosh. Alternatively, I will just panic. Sure. Oh yeah. Rules color to contained. Yep. So now we need to actually parse stuff here. We got color. That will be our key in the color to contain map. But we now need to inverse rules. So for each rule, we need to take a number and then take backs. Oh, here actually it probably will be regex time, right? So no other backs. Then we just insert color and an empty vector. Alternatively, we need to pass each rule. For that, we will need to do the stuff that we already did with the whole lazy static regex stuff. So I will just copy it somewhere here. Number. Then we have space. We have color, which will be bright white, for example. Then bags or bag. Which can be optionally terminated with either this or this, so comma or dot, and this whole stuff is repeated multiple times. Oh. Or actually I don't need to go as complex, right? Color bags. Yeah, I think that should be already okay. Because here we don't have any space. Okay. Rules split. We are splitting on commas. followed by spaces. And then for rule in this stuff, what we do need to do, we need to faded block. We need to execute the regex stuff, so I will look this up because I think I will never remember this. So captures iter, this thing is, right? And this can be optionally actually ended with dot. So if it's a dot, then we'll allow this. Captures iter. Yeah, just do next on this stuff. And here we have some of rule. And then, oh yeah, by the way, I need to fix my main because I forgot to update this number. Yeah, now it's better. And then I just can use capture name, I guess. Name number. Color. Gosh, it looks so ugly. Some number. Some color. Or I can simplify this stuff a bit. I can do let if. Or if let, more precisely. Here I need to do none. Actually, here I can also do to simplify this a bit. Oh yeah, of course, captures iter rule. So finally, if we got the rule, name and color, we then can do contained, which will take color, will be color, count, yeah, I want to be consistent about my naming. Count then will be, gosh, I think it is, it's usize, so is it, count parse usize, and I guess unwrap it, something like that. But now it will be annoyed, yes, because it's match, I think. Oh yeah, to string. Then for count as well, of course, we need to do string parse. So that's contained, and then we just do color to contained, and here we need to get an entry because we need to push in the end of the vector, right? If we don't have a key there, or like if we have a key. So we get entry for, this is rule, this is color. Oh, contained color. Yes, that's, so we take color and we do on insert where we put vector. That will give us mutable reference to the stuff that we just pushed. So that will be contained. This should be mutable, yeah, mutable reference to a vector. And then in contained, we can call push and put contained. Oops, contained vec. All contained. Let's do it like that. Okay, we wrote something that looks rather monstrous. What don't you like? I guess, oh yeah. Actually, let's do it more simply. So we insert color, which will do toString here. Now here it will be unhappy about that, so we need to do toString. Yep. So now we can in principle try to write our first test and see if it parses the input correctly. Oops. So how it's called, rules parse, and we just do sample input. Here of course we don't wrap, and now we got through stuff. And for now I will just do this, I guess. I wonder if it will print, because normally you need to do, yeah, it does. So nothing happens. Bags contain, I wonder why. Let's add quick debug here to see, and rerun it again. So lines look correct. This part works. Color and rules. Yeah, those are references, so should be all right. Dotted black, no as backs, vibrant plum, 5 faded. Okay, that looks good. Oh, of course. I did this without actually specifying what I want to do, which will be everything really. So let's try. I essentially didn't match the colors itself at all in the regex. Let's try it again. Oh, that looks better. So muted yellow contains 2 shiny gold backs and 9 faded blue backs. Okay, splendid. Let's add some quick checks here that we did parse everything correctly. So Let's make it a bit simpler. Let's call it inner. So that it's not as awfully mouthful to use. And then we can do so we can make sure. And here we can do light red contained bright white, one bright white and two muted yellow. Yes, it doesn't like it. Oh yeah, because of course we also need to put it in sum. So, and let's check that faded blue has nothing. So it will be an empty vector. Dotted black as well. Yeah, of course, those should be also references. And bright white back contains one shiny gold back. So let's check also when we have only one instead of multiple here. So bright white, shiny gold. So, and overall, how many rules should we get? Rules in a keys lengths should be 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's run our test. We should get no debug output and ooh, something broke. Left 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. I wonder. I wonder if it will work like that. So muted yellow, bright white, shiny gold, dark orange, dark olive, light red, vibrant prune, but faded blue, not. And dotted black, not. Contain, let's see, I guess it's our regex thing. So bugs contain if rules equals to no other bags. Oh, we missed dot here. So now I guess. You see, it's good to write tests sometimes because otherwise I would have debugged it for some time. Okay, now our parser works. Now we can try to finally solve this stuff. As usual, I spend way more time writing parsing logic than actually implements in the solution, I guess. Well, we will see. I haven't implemented it yet. Maybe this time I will be super slow. So what do we need to do? In essence, we need to turn stuff around a bit, right? So if we count, so in this example, the number of back colors that can eventually contain at least one shiny gold back is 4. It should contain at least one shiny gold back. So essentially we need to go from shiny gold back to like another back color that can contain it. And then for each of those we need to go further for all the bags that can contain them. And then we essentially, when we get the whole thing, we need to do a set of that and do a length of set again. So hash sets, as typical, are our best friends. Now, hash map is, in this case, it goes from one color to contain thing, right? I wonder if numbers actually matter. Mazerbacks. And hold. So in the first part, at least, numbers don't matter, it seems, because as long as we have containment, we can go to the back. Now, if you try to revert this thing and try to go through all of them and say, okay, who can hold shiny gold bag? Who can hold which kinds of bag? Essentially, we will probably need to move this hash map from going from like the bags that contains to the contained bags in another direction, going from contained bags to the bag that contains it, to all the bags that can contain it. So let's try to do that. So we parse our stuff, and then we need to invert this hash map. Which will then be hash map from color to a vector of colors, right? Yeah. And this will be then new hash map, and it will be mutable, of course, because we want to fill it in. And then for each of those inner, we do iter, and we say for container to contained, we need to do contained in insert. Oh, and that will be, of course, hash set, right? So we need to insert container is this stuff, contained is contained. Oh, and then we also need to go for each contained. And here we then can do contained in. I guess we will need to take an entry to our key, then will be contained. My naming here is so bad. I really wonder if I can improve it somehow, but okay. contained will then we can do or insert, which will be hash set new. So that will be immutable containers, mutable reference to a hash set. Yes, hash set of strings. And then containers, we can insert container. Now it doesn't like some stuff. Contained color. Right? Okay. So that contained in. Let's try to do this stuff. So let's add a function here. Part one solved. Test, I mean. And we can do, let's sample input. That's a lot of typing. And then we can do solve sample input. Now I will just assert that. We know actually the answer already. So for this part is 4. So sum 4. And this will be a test. So shiny gold can be contained in bright white. Let's look at this stuff a bit more. So that's our inverted map, right? We should still get 1, 2, 3, 4, 5, 6, 7. In this case, because some of those cannot be contained. The dark olive can only be contained in shiny gold. Dark olive, let's verify. Yep. Faded blue can be contained in muted yellow, dark olive, and vibrant plum. Yep, and bright white. Yeah, so it seems that we got our logic right. Shiny gold can be contained in bright white or muted yellow. Yeah, bright white, muted yellow. Then, for example, dark orange can contain bright white, dark orange. So you can see that my idea is that we go from shiny gold, we get those, we expand them, we add those, we go for those, and we go, etc., until we got to, until we stop, essentially. So, this is essentially transitive closure, isn't it? Yeah, it is. So actually that is a nice function that we can extract. So we can say so this is contained in. Actually, I can even make it an instance method. of the rules in, right? So we got parser and we get contained in, which takes a reference to self. Yeah, we don't need another thing for rules here. Yeah. We got contained in. And now we can start to do the recursive stuff. So with our inverted map of which bags can contain which other bags, I will just do this so that it's a bit easier to type. We should get in essence, we should get a hash set, right? Of colors. And then we probably will have some kind of transitive closure inner. Which takes colors. Yeah, this will be reference, of course. Color. I'm a bit dumb. I need to have color. I guess. So okay. Now this stuff, I'm coding Advent of Code. So Advent of Code day 7, Handy Haversacks. You can read the task on the website. I just did parser and now I'm solving the part 1. Part 2 will follow, hopefully. We're doing some magical recursion because we have those rules for which bags can contain which other bags. And we can invert them. And essentially we inverted that stuff to figure out, okay, where bug can be contained. And now we need to calculate transitive closure to answer the question, which is how many different back colors can eventually contain the back colors that is our input essentially. So here we essentially need to do contained in and then do for, I guess, get. Oh yeah, we need to do colors, iter, I guess flat map, because that will be for each of our colors. Get color, and color will be, and do contained in color. No. Yeah. And then we can collect, I guess. Oh no, we need to call ourselves recursively here. So contained in, and then color. Okay, I really wonder if that will actually work. But let's try it out. So far, at least the type checks, which is usually a good thing, contained in. But I'm always afraid that this will never terminate. Let all colors. So can contain shiny gold colors. And we do shiny gold here. Yeah, we need to have a reference here, and shiny gold will be, yeah, we do to string, then we do reference as well. And then we can do links and some. Oh yeah, and of course our magical thing to comply with REPL stuff. So I want to quickly do debug on this stuff. Yeah, we need to use reference so that we don't consume stuff. And now we can try it again and see. Is it what I expected it is? Is it? Oh yeah, Stack Overflow. Okay, we forgot some termination thing. How, so yeah, we get this transitive closure stuff. We take contained in, and then we go for shiny gold back directly. We generate colors. Oh, we also need to exclude the stuff that is already considered, right? Can we actually pass also mutable reference to our color? Like if I actually we can probably solve it a bit easier with iterative version. So I'm thinking contain shiny gold. I will just hard code it. I will say and then I will just actually I will take contained in get shiny cold. I will make it to a string. And then I will collect it as hash set. Oh, it's already hash set. But then yeah, Rust is not the easiest language, that's for sure, Aris. But stick with it. I think at first it looks harder than it really is. After some time, you get used to that. Shiny gold colors. Okay, I will do this stuff for now. And here, actually, let's also make it a bit smaller. And okay, we got the original hash set, and then we just do while. What will be our rule, right? We can just go through. No, we cannot go through all rules. This is like our original input. And then we probably have considered. Like my brain is slightly breaking because I'm thinking, how can you actually calculate this thing? Okay, it's time to look up the algorithm, I guess. So of course, so what does it do? Will be has the shortest distance. Oh god, this is a bit too complex. In essence, maybe I'm also overthinking it a bit. So like when we have this stuff, can we also create here things that will say checked and will be like hash set as well? Too many hash sets. I feel that this shouldn't be that complex and I'm probably overcomplicating it. So contained in so if checked contains color, transitive colors. So if check doesn't contain color, then checked insert color. Can I do one dereference here? And of course, checked. And here we need to do the string. And that should return transitive colors. So that's kind of like termination condition, right? If we essentially keep track of stuff that we already checked. Okay, then I guess let's try to hope that this works. It still overflows. I really wonder how and why, because we don't have that many things here happening, right? Maybe we just... maybe it's because we... Oh, I see. Because we tried to goes through multiple things, I guess, at the same time. Oh, we have one color. Transitive closure inner. Let's do a quick debug here with colors to see if that works. And yeah, I will also fold this stuff because otherwise it's super hard to read. So yeah. Oh, shiny gold, shiny gold. Okay, it doesn't progress. Why doesn't it progress? Oh, transitive colors. What am I doing? I'm trying to return this stuff. For each of the colors, we need to return contained in get color. Which can be so this then will be a hash set of strings. And for each of those strings, I then need to do the color. So we insert checked here. And here, gosh. Transitive colors. So iter collect vector. Okay. Is that it? Let's try to see. So zero. But then at least we start going through them. So we start with shiny golds and we do bright white, muted yellow, dark orange, light red, dark orange, blah, blah, blah. The only problem that we don't actually return everything, right? So we... Here we return empty vector. Oh, so it seems in the end what we need to have is, so we do this, we do transitive colors, which actually don't need to return anything, and in the end we will, everything that we try to reach will be here. So for now I will just ignore it, and instead I do checked, and I guess if I run my test now it should actually work. No. Sum 5. We start with our original color, right? So if we look at the we can do remove our original color. And we can just return checked. And then here we don't need to return any vectors. We just terminate. Terminate. So here we don't even need that. We don't even need this. We then can do for color in colors. Of course, yeah, this now returns unit, this returns unit. So our logic then becomes way simpler. We don't need that. We just do transitive closure inner. And then we should get the result. Now let's see. Yep. That seemed to work. So we can now finally solve our task. Let's, yeah, by the way, I can also remove the, do I still have debug somewhere? Yeah. Oh yeah, so can contain shiny gold, bright white, muted yellow, light red, and dark orange. Okay, that matches. And yeah, for those who are joining now, we are still solving the day 7 part 1. It was more complex than I thought, or like more precisely, I was dumber than I expected. But in the end, it seems we did it. The only thing we actually need to now pass the answer. So I will say, like, I will make this assert fail. I know that it won't be 0. Puzzle input will be, oh, it's actually just D7. Let's run it. And 226. Let's see if it indeed works. Yeah, we solved it. Okay, let's add it to our test and do the run now. Okay, it works. Everything passes. Part 1 solved. Okay, whew. That was a bit more complex. Now let's see what part 2 holds. It's getting pretty expensive to fly these days, not because of ticket prices, but because of the ridiculous number of bags you need to buy. Consider again your shiny gold bag and the rules from the above example. Faded blue bag contains 0 other bags, dotted black bag contains 0 other bags, vibrant plum bag contains 11 other bags, 5 faded blue bags and 6 dotted black bags. Dark olive bags contain 7 other bags, 3 faded blue bags and 4 dotted black bags. So a single shiny gold bag must contain 1 dark olive bag. Okay, let's also look at sample because I'm getting confused with all the bags already. So a single shiny gold bag must contain 1 dark olive bag. Shiny gold, 1 dark olive, 2 vibrant plum, okay. And the 7 bags within it. Dark olive contains 3 faded, 4 dotted black, yeah, 7, plus 2 vibrant plum bags, 2 vibrant plum bags, 5, 6, and the 11 bags within each of those, so 32 bags. Of course, the actual rules have a small chance of going several levels deeper than this example. Be sure to count all of the bags, even if the nesting becomes topologically impractical. Here's another example. Blah, blah, blah. A single shiny must contain 126. Ooh. I guess it's like how many individual bags required inside your single shiny gold bags. Shiny gold bag. So before we counted like inverted thing where we were checking all the bags that can eventually contain shiny gold bag, and now we need to actually use the first thing with like rules saying that this, oh god, how many bags are contained, we need to count it for shiny gold. Our day 7 input is interesting. We may encounter problems with our recursion because we may end up with stack overflows. But first, let's see if it will work. So we have those rules for contained in. I think it's actually, will it be like even recursive? We can just follow up, I guess. Okay, since it may be a lot of stuff, let's try to write iterative versions that follows it forward, this rules structure, which is essentially a hash map from colors to vector of contained, and contained is just color plus count. So let's, like, if you try to write an iterative version of recursive algorithm, what you typically need is a stack. So on this stack, we will have to satisfy, meaning rules to satisfy, where it will be just a vector of things. In this sense, we don't care about uniqueness, so it's not a hash set, and it's mutable. Now we start again with shiny gold. Of course, it's very easy to make it a parameter as well. and we just push it there. Now I will return none to avoid errors. And then while to satisfy is not empty, while we still have rules to satisfy, we need to continue counting, right? We will have mutable count, which starts with 0. Yeah, because we don't count the original back from which we start. And then essentially what we do, for each to satisfy rule, we say, yeah, we also of course need to parse input. And by the way, that we can make here. Here we can also simplify our code a bit by moving stuff contained in here to be to not extract rules themselves. Well, I can just put this string here as well, doesn't matter. And then essentially we say to satisfy pop. Thankfully, Rust's vectors are also stacks, so it's very easy to use them for this kind of stuff, where we get an option. Ooh, we can actually do, that's even more beautiful. We can say if let some rule equals to satisfy pop. So that's our rule. We then can go to rules in the get, let's say color better. Is it actually color 126? No. It's not one color. It's already a number of things, right? Because we need to multiply by that. So that will be containment, I guess. So contain this color plus count. And then here it will be rules get shiny gold to string. And what else is there? Yeah, that will be get found for struct. Oh, inner. That will be a vector of, yeah, I want to unwrap it because I know that there is something with that. I don't care about correctness that much here. And then we have a vector. Oh yeah, we already have vector, so I'll just clone it. Okay, so it's vector of contained. I want to dereference it. Yeah. So this is a vector of contained, and then that will be contained, not color contained. And then essentially we need to multiply stuff. Oh god, now I'm getting again confused because complexity here will be that we need to do it n times, right? So like for each of the banks, I need to count this stuff. Will it work like that? Like doing this kind of iteration simply? Oh no, I think it won't actually. Okay. I will try then recursive solution for now, but that won't be pretty. Gosh. Is it really so complex here? Because so I get like shiny gold back will contain 1 dark olive, 2 vibrant plums. So if I go dark olive, I will count it as 1, and I will put dark olive on top of a stack. But then the problem is that if I say 2 vibrant plum, actually I can just put 2 copies of vibrant plum on a stack, right? And then for each of those, of course, I will need to calculate this stuff multiple times, which is a bit annoying. I guess one solution would be to use something like memoization, right? Where you calculate it for each of the colors, and then you can, yeah, it's easier than to solve this. Yeah, because right now, if I go with iterative solution, it will be hard for me to match the color with the number of things it contains. If I go functional recursive way, then I can memoize, which means I can also have a hash map that matches each color with the number of, like, total number of all contained bugs within it. And then I can, in principle, calculate stuff way faster. Let's go with the naive solution for now and see if it works, because that should be easy to write, right? We can start with just putting the stuff multiple times. So contained, we say contained count. And then we push on the stack where pop takes we actually need to do it like X times. So for 0 contained we need to do push contained color found struct. But here I don't then use count. If I use this, so I pushed like each contained thing 1, 2, blah, blah, blah times. Like I say, okay, I have 3. Then I push 3 faded blue. Each of those with 1. But then I need to so that will be contained count 0, or actually 1. Contained count. Oh no, I can avoid the whole loop here, right? I can just say contained count. That will also loop, I think, because I popped it and then I put it with the same number of things. So we need actually to string. Can we write a simple function that will move from contained to n strings, which will be then contained, and it will just return a vector. That also is so terrible because it's so much copying. Oh gosh, it will be super slow, I think. Contained, and we have then Do we have something like fill, I think? Oh yeah. Oh god, there's syntax for that. I'm so dumb. So there is syntax for that, but there is no function for that. So contained color. And then we do it color count, I guess. Yeah. So we get this, we unwrap, then we map, which H is contained. What am I doing? And then we collect into a vector. No, I will just do reference here then. Why it is dynamically sized? I'm so confused. So we take, because I'm doing the reference here. Okay, that's how it looks. So now we got like n of each thing. So for shiny gold, we get like one string dark olive, and then we get vibrant plum in this to satisfy vector. And then for when we take one of those, we can add it to, we just say color then. We always add one. And then we push this stuff. So we take rules, we take inner, we take get, we take color. We essentially do then this stuff. For now, I will just copy it because to n strings. I would just say for. So then contained is a reference to contained, and we can then say to satisfy insert append items. Let's contained to n strings. It should be mutable, and that probably should be a mutable reference. And then in the end we just report count. So, okay, that looks quite terrible, I think. But we can try it and see if it will ever terminate. I wouldn't be so sure about it. Let's first start with our sample stuff and see part 2 solved. Option unwrap. Oh, I guess we sometimes get empty stuff, right? We get empty list of things and then it doesn't work. So where does it fail? Cargo format. Interesting. Okay. We call unwrap here and here. Let's just do it. Instead of unwrapping, and then we can call it all contained again. So now we can try it again. We still have, what? We take inner and we then get shiny gold and shiny gold. Let's do just expect. Didn't get anything for shiny gold. Oh, I did this. Okay, I'm so dumb. I didn't need that. So let's try yet again. So sum 1. Okay, that's definitely not what we would expect. We need 32. So why do we get 1? Do solve 2. To satisfy append. Inner get color. We do all contained inner. So let's just do this. Let's do debug color, right? And see if rerunning this test. We only get shiny gold, I guess. No, vibrant plum. Okay, we get vibrant plum. We do count +1. Then we do, if you look at vibrant plum, what happens? $11 as a bags. So we then rules inner get vibrant plum. And that should return as a bunch of stuff, right? We can do, for simplicity, debug rules to see what we will get there. We shouldn't move out of it. So vibrant plants then has 2 things. One of them will be dotted black. I wonder if that is the reason, because we pop it, we then do all contained for each of those. We do to satisfy append items. You can also do this. And then, yeah, by the way, that I can also fold so it doesn't annoy me. Also, it actually works. It adds faded blue and then dotted black. But then it still stops at 1. I guess faded blue and dotted black, they both terminal, right? Yes, they're terminal. They return 0 when you use them. So if it's 0, I guess then when we go through them, it pops everything out. But why we only add vibrant plum and why this don't increase stuff? Let's also add this so that we can actually see also the state of our stack. So we got the rules, then we get to satisfy these 2 items. Oh my god, of course it's while let, it's not if let. Okay, so this stuff all looks correct to me. Now, yeah, we'll also remove debug for rules and let's see if it will work. So essentially I just did like 1 iteration, of course, then it didn't increase. Sum 32. What's the right answer for this? 32. Okay, so it works. Okay, let's see if it will work with actual input, right? And we can then contains and string. We also can remove this debug thing here where we do contained. Yeah, here we don't need it. And then we can run it again. Or actually, I will do cargo run and I will use our beautiful interpreter here to see. Oh wow, it actually was quite fast. Is it correct? So let's see. Woo, we solved it. Okay, iterative solution worked. I think it's not the most optimal way, but at least we solved day 7 now. Whoa. That was way more intense than previous days. Let's add the test here, make sure that all our tests are running correctly and that we don't get, ooh, something failed. Of course, we forgot to put it solve2 here instead of solve. Okay, tests work. This stuff we can remove, and this stuff we can remove. So quick analysis, what have we done? We implemented transitive closure algorithm on inversion of a hash map here. So contained inverts the hash map with rules that we created. And then transitive closure uses recursion to calculate transitive closure of that contained in hash map. And for the part 2, we, instead of going with recursion, we went with iterative algorithm, where we created a stack of colors that we still need to create like bags with those colors, count bags with those colors. Starting with just our bags that we need to put inside our shiny gold bag. And then for each of those, we found rules for them, we expanded them, added the corresponding number of items for those bags there. By the way, I think okay, yeah, we use it in 2 places, so I wouldn't actually factor it out, but yeah, we wrote this very simple function that just duplicates the amount of like the colors that we need multiple times, and then we put everything on the stack that we have, and we terminate when the stack is exhausted. As usual, while let and if let statements make it way more beautiful than in most other imperative languages. So pretty cool stuff we did today already. Let's quickly commit this, and we will continue with day 8. Oh, of course. So picture becomes more and more interesting. Handheld halting, day 8. Your flight to the major airline hub reaches cruising altitude without incident. While you consider checking the in-flight menu for one of those drinks that come with a little umbrella, you are interrupted by the kid sitting next to you. The handheld game console won't turn on. They ask if you can take a look. You narrow the problem down to a strange infinite loop in the boot code, your puzzle input of the device. Oh my god, we're getting there. Okay, this stuff is amazing. We are doing virtual machines like last year. That was my favorite part. Sorry, I just cannot contain excitement about this kind of shit. And in the boot code of the device, you should be able to fix it, but first you need to be able to run the code in isolation. The boot code, when I had this task about validation, I thought, okay, this sucks. I don't want to do it. I will die. But this thing is amazing. That's what I needed. You should be able to fix it, but first you need to be able to run the code in isolation. The boot code is represented as a text file with one instruction per line of text. Each instruction consists of an operation, accumulate, I guess, jump or nope, and an argument, a signed number like +4 or -20. And by the way, last year, that was a big thing for us because I was implementing it in Elixir and you don't have like types and stuff. You have type specs, but it's not quite the same. Here, I think we can actually start getting some really nice benefit from Rust because it's statically typed language with very good type system, very expressive type system, so we can model stuff quite precisely, and then we should have way easier time when we will need to expand it and refactor it. I would imagine that we will be having this like long-running things that periodically, like every next day or something like that, we will get more tasks with this virtual machine. Each instruction consists of an operation and an argument, a signed number like +4 or -20. Accumulator increases or decreases a single global value called the accumulator by the value given in the argument. For example, accumulator +7 would increase the accumulator by 7. The accumulator starts at 0. After an accumulator instruction, the instruction immediately below it is executed next. Jump jumps to a new instruction relative to itself. The next instruction to execute is found using the argument as an offset from the jump instruction. For example, jump +2 would skip the next instruction, jump +1 would continue to the instruction immediately below it, and jump -20 would cause the instruction 20 lines above to be executed next. Nope stands for no operation. It does nothing. The instruction immediately below it is executed next. For example, consider the following program. Nope, jump. These instructions are visited in this order. So we start with nope. Then the accumulator is increased from 0 to 1 after acc1. And jump +4 sets the next instruction to the other accumulator +1 near the bottom. So jump +4. 1, 2, 3, 4. Yeah. After it increases the accumulator from 1 to 2, jump -4. Execute, setting the next instruction to the only accumulator +3. it sets the accumulator to 5 and jumps -3 causes the program to continue back at the first accumulator plus 1. This is an infinite loop, which with this sequence of jumps, the program will run forever. The moment the program tries to run any instruction a second time, you know it will never terminate. Wow! Immediately before the program would run an instruction a second time, the value is in the accumulator is 5. Run your copy of the boot code. Immediately before an instruction is executed a second time, what value is in the accumulator? So we need to model the virtual machine, obviously, and then we will need to use this termination condition to report the accumulator value. That's our program. That sounds really, really nice. Oh, man. Let's quickly do our typical thing. I probably need to really improve my auto generation of stuff, but I'm also becoming quicker at that. So we will add the stuff here. And we'll put our input here into A8. We will copy this stuff, make those none. And finally, we will do the test stuff. So do we want to do something with sample input? So here is our sample answer. It will be 5 in this case, because there's only, it sets the accumulator to 5 and jump -3 causes the program to continue back. Okay, so we can also do sample. And this will be our sample program. It's a bit easier to reason about. We can then also look, we probably will need to do parser, right? So this stuff you can also just copy now. Yeah, we'll just do this. Oops. Of course, I need to make this as well, so that we can already start running some stuff. Yes, so that's our input. Now we need to do the virtual machine. I will toggle sense so we don't have as much visual noise on the screen. How do we model our program? So we will have instructions, right? Do they call them? They call them operation. And operation can be ACK, it can be jump, it can be nope. So here you can see that Rust type system has this handy feature called enum, so algebraic data types. So this will be one nice thing. Debug, clone, partial equality. We can just derive a number of things for that already. Then we will have just a struct called instruction, I guess. I will call it ins, just for brevity, because then we will have like the list of things there. Vector of things which we will need to probably read, and then if we call stuff a bit shorter, it will be a bit easier for us to see if our parser is correct as well. And there you essentially have two things. We have operation. Actually, I will even start with something super simple, right? I will start with operation and well, number is just I64, right? I guess. So this is tuple struct. You can see that we have like those argument and operation here. They had different types, so it's pretty easy to distinguish them. And then we have then we essentially have a machine. So machine will have the accumulator value, which will be I64, and it will have a program, which will be a vector of instructions. And now we can also do all this stuff, and here we can also do this stuff. Why not? And then we can start implementing stuff for machine. So we can implement parse. I think I will become very good at parsing things by the end of Advent of Code. We do trim and then we got each line. So this will be our instruction. And then each instruction we can just say instruction split. Also can do trim end on that. I know it will not have already the new line stuff, so we can avoid, we don't need to do it. We can then just say split ASCII white space for, I wonder actually if it's faster than just splitting for normal one symbol white space, not sure. We'll need to check, but for now I just will use it. And this stuff will return an iterator that I will, again, using my favorite trick, I will collect it into a vector. By the way, I don't know if this is really the most efficient way to do it. I would guess not, but it just looks way more expressive to me. So we will have instruction and do they call it argument? No, operation and argument. Let's call it like that. If it's something that we don't expect, we just panic saying unexpected line. But here we can also provide parse method for op, right? Let's do it non-panicking just in case. Or actually, nah, let's always panic. Let's be very simple about this stuff. So input can be nope. One interesting thing about Rust that it's algebraic data type create a namespace, so you need to import them specifically. Just do nope. If it's arc, we do arc. If it's jump, we do jump. And if it's something we don't expect, we panic saying unexpected op. Oh, sure. Okay. Then here we can say parse operation. Actually, let's be very short. Op and arc. Op. And for arc, what do we do? So I guess trim start. Trim left. No, trim start matches, and matches can be then, because about plus we don't care, and then we can just do parse, and we can parse it into I64, and then you can just expected arc. And here, yeah, we also will need to create a mutable machine. Machine will be, original accumulator will be 0. Program will be a vector. Oh no, we don't need to. We can just say let mute program. It should be an empty vector. And then we just do program insert, oops, push, and here we do instruction op arc, and in the end of this we can return a machine with accumulator set to 0 and program. Another cool feature about Rust is that it shortens those labels. So if you have variable with the same name as label instruct, field instruct, you don't need to write it twice. So you don't need to do program. What doesn't it like? Sure. Oh, okay, it doesn't allow. Does it allow like expect error? I wonder if we can just pass a... Oh yeah, that works. Okay. So let's try to parse our stuff now. It's input, and then we can just do debug machine. So, and it seems that we parsed our program. So accumulator is 0, so we start with no operation 0, accumulator plus 1, jump plus 4, accumulator plus 3, jump minus 3, accumulator minus 99, accumulator 1, jump minus 4, accumulator 6. Splendid. I will just copy this stuff verbatim and put it here. You see that now because we were so simple with the naming, our machine structs are actually quite readable, so that's good. The only thing that I don't like is the Rust format always adds Australian commas. But okay, what can you do? So what do we need to do now? Now we just need to implement an interpreter for this thing that will run the program, and then will terminate when we execute instructions second time, right? So let's start with interpret till repetition. Or like, I think we just do, first we do execute next instruction, right? So advance is how I typically call this thing, which takes immutable reference to machine. By the way, we will also need to have instruction pointer, which at first will be pointing to the first instruction, which is 0. This will be usize because vector doesn't have negative things. And instruction pointer will be 0 in this case. So then advance doesn't take any arguments because instruction pointer points to the instruction we need to execute. And it doesn't return anything either, I guess. Will it then make sense for this particular task? Because that's usually how you do interpreter. You interpret like one step, and then you can run it in a loop. But in this case, okay, let's just do it. Run till repetition, and we will just return the stuff that we want, which will be before the program would run an instruction a second time. Then what we do, we will just save current accumulator, I guess. Structure a second time. We can just save indices, right? So I always call this stuff something like seen or visited. So seen will be a vector of instructions, also mutable. And then by the way, here instruction pointer will be at 0, right? We essentially do what? Oh no, it will be hash set again. Dump. So hash set new. Yeah, hash set is definitely the most favorite structure of this advent of code. So then we do self program. We get self instruction pointer. Yeah, sure. Which will be just instruction. So let instruction if instruction if sin contains this sin. So if sin doesn't contain this sin, then sin insert. Okay, I see. So let instruction will be this. this is. I'll just do. Oh yeah, instructions that need to be hashable. So hash stuff, and we need to add it on here, which means we also need to add it here. I don't think we need hashable machines yet, but who knows what awaits us. Found expected reference, sure. Sure. We clone, we insert. And what do we do next? Now we can actually do advance. So advance just takes mutable self. So that will be while loop as well. And here for advance, what we do, we just say clone. We advanced self, and yeah, of course, self advance. And this stuff, by the way, then we can just do it like that. And then this stuff we don't need, because then once this loop terminates, we know that we will not execute the next instruction, so we can just say self accumulator. Right? And now we need to actually Аня, мне очень приятно тоже. Thank you. So advance will be our actual interpreter because it will essentially look at the current instruction pointer. So we will say self-program self-instruction pointer. We will then do, does it like, yeah. We will then need to look at each of the instructions. So we'll look at if it's nope, we ignore argument. Now we just do nothing here. Another instruction will be accumulator. And third one will be, or actually I can just do 0, right? Because then it will be easier. It will be nope, acc. Let's call it instruction for simplicity. And then this. And then we will also have jump. Do we want, for simplicity, make instruction copy? Instructions so far, they contain i64, which is copy. I used to be on Twitch, so with Twitch I wasn't able to find any viewers for quite a long time, so I decided to give up and move to YouTube, which so far worked way better. Yeah, I probably need to remove the old link to Twitch, or maybe also try to stream there in parallel. Not sure what is better. I think Twitch has way better interface for streamers for sure, but YouTube has way more people, especially people who want to see some programming compared to Twitch. So that's why I'm here nowadays. Okay, so now it implements copy. which means, yeah, we get this. If it's nope, the only thing we do, we advance our pointer, our instruction pointer by 1. By the way, I really wonder what will happen if we will run out of stuff. For now, I will not try to process because I think we won't with our task. But let's just say fix me. Avoid running out of program. This acc, we add or subtract from the accumulator. So here it will be two things, right? It will be self accumulator plus our instruction argument, which is 1, or alternative, and then we do self IP plus 1 as well. And for jump, we do self IP plus arc. So now I'm also thinking about maybe matching it and saying op arc, because then our code will be a bit better. And here, yep. IP as usize. So that, okay, that is a bit unfortunate, right? But at the same time, it kind of prevents us from getting out of program index, I guess. For now, I will just go with the simplest possible thing. Let's do I64. Then we will here need to cast. But at least... So we can say... We can simplify this code as well a bit. Instruction. So, okay, now it looks better. And we can try to run this. So let's add logic. Part 1 solved. We will do the same thing with input. We then do... Oh yeah, we actually need to put it here in the function. So we parse the machine, and then on machine we execute accumulator before repetition, which will be solution, and then we just return it as solution. Machine, of course, should be mutable in this case, because we are doing Rust and we want to try to go mutable this time. Before that, always done some functional stuff, so immutability, which is typically better and makes for simpler code, but in this case I want to try to write a bit more mutable stuff this time. And then we can do solve input, that should be a reference, and here we do assert equal. What is our expected thing is 5. So let's see. Something failed, I think. Some 0. Okay. Do advance. Sin insert instruction. I think we should not do... Yeah, we have 2 accumulator. Okay, that's rookie mistake. We have 2 accumulator plus 1, so it stops too early. It stops when accumulator is 0, so plus 1. It's still wrong, I think, but like jump for 1, 2, 3, 4. I also think maybe my logic for calculating instruction pointers is a bit off. Okay, so instead of putting instruction itself in scene, we need to put self IP. And then we don't need to, we just use instruction pointer. So this way we will know if we actually in the same instruction, meaning in the same position in the program, right? So if you try to run it now, yep, we solved it. So of course we still need to run it on the bigger input, right? Let's though do it with our REPL. So day 8, 1614. Yep, we solved it. Let's add it to our test. 1614, day 8. Run all our tests to make sure that they are working. Yep, they are working. And we can continue to part 2. After some careful analysis, you believe that exactly one instruction is corrupted. Somewhere in the program, either a jump is supposed to be a nope or a nope is supposed to be a jump. No ACK instructions were harmed in the corruption of this boot code. The program is supposed to terminate by attempting to execute an instruction immediately after the last instruction in the file. Instruction immediately after the last instruction in the file. By changing exactly one jump on nope, you can repair the boot code and make it terminate correctly. For example, consider the same program from above. If you change the first instruction from nope 0 to jump 0, it would create a single instruction infinite loop, never leaving that instruction. If you change almost any of the jump instructions, the program will still eventually find another jump instruction and loop forever. However, if you change the second to last instruction from jump -4 to nope -4, the program terminates. The instructions are visited in this order. So nope 0, accumulator, jump, 4, 5, 6. And here that's the order 3, 4, 5, 6, 7. After the last instruction, the program terminates by attempting to run the instruction below the last instruction in the file. With this change, after the program terminates, the accumulator contains the value 8. Fix the program so that it terminates normally by changing exactly one jump. On nope, what is the value of the accumulator after the program terminates? So, how do we approach this? I guess we need to first of all, of course, every time we have this like okay, in sample, what happens? We go like down, 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 we jump down, and then we jump up. So that may be one like way to figure out which jump we should replace. However, in this case, so I'm not sure that it will be generic, right? I wonder if we can record the trace. So Let's do a vector. We are doing a vector of positions here. So I just want to trace the program so I know that what happens there. So it's one thing, and here I can also do trace, should be an empty vector. And then when I go with advance here, what happens, because I only need to solve my input, right? I don't need to solve it in the most generic case. So we need to see, because maybe if I just trace it, that will be obvious. So if trace is set to true, we add stuff to this trace vector. And here I want to trace stuff actually. So then here I want to what I want to do. So in solve, accumulate there before repetition. I just want to debug my trace and see what happens. Yeah, we don't want to move. We just want to debug. So now when I run it, I will comment the stuff out. And I will, of course I need to. So that's the trace of my bigger program. If you look at that, let's take a pic. So we go here, and then we jump way down. How many instructions do we have? We have, I wonder if it will show it to me. So this is like, oh, that's sample. I need day 8. 633. Okay. That's a lot of instructions. We go here and then we jump up from 221. In principle, we can of course also try to experiment manually, but I think there are several places where it jumps up. So it jumps up here, then jumps down, it jumps down, jumps up here, jumps down here, jumps up here, like way up. Yeah, I guess manually it will be pretty annoying to try to solve it. But still, I like to have trace capability here already, and it was so easy to implement. I will keep it, I guess. We can just try to run it. We can just try run multiple copies of the machine, right? With like different, replacing knobs with jumps. I also wonder if instead of trying to return trace here, I can also try to look at the total count of knobs and jumps to see how doable it is. Solution, oh, sorry. Machine program, I guess. we have a vector of instructions, so we can do iter don't we have group by partition, or maybe it's only on slices? Let's see. Ooh, we don't have group by apparently. Okay, are chunks and stuff. Well, we can just filter. So we do iter and we filter, and this will be instruction, and then instruction. Actually, I can even match it here. So op, I don't care about argument. Then if op equals to jump, or op equals to nope. Actually, how do you even change jump to nope? Will it? Oh, because then we don't know if it will work. Like we don't know the argument that we need to. Ah, no, nopes also have argument, right? So we only need to change this part. Okay, makes sense. If we do this, and then we just do count, and then we can do debug. That will be the thing. Sure, you can. Let's dereference. Okay. So now, when I run the test for the first part, $286. Oh God, that's a lot of those. So we will have 286 programs to run. Can we do some fancy threading here? Yeah, I guess we can. But first we will need to add a couple of functions to our couple of methods to our machine thing. So first of all, yeah, avoid running out of program. So I guess this thing will also need to return bool. We'll just let's returns true if the program has terminated. But Tencent runs instruction below the last instruction in the file. So yes, I will be prudent here. I will say if it's less than 0 or its self AP is larger than self program length or equal to relay true. Yeah, we can actually do this like that. Is terminated, which will be then return bool. Doesn't matter in this case. And then we just do is terminated. No, we don't even need to do the check here, right? We can just do it here. So we have termination check. And then so this is like more specific stuff that we can actually move to our solution, I guess, because it's not really thing. Contains machine IP. So I think that's a bit better because this is really specific to this function only, not really to the whole logic. So now in solve 2, start with the same stuff. After the last program terminates, but attempting to run the instruction below the last instruction with this change after the program terminates, accumulator contains the value 8. So then we will need some facilities for running stuff in parallel. Do we do rayon? I guess we can. I think I never actually used it. So that will be an interesting experience. So you can do par iter. I wonder if they have like first terminated thing. If they do, then it will be perfect. If not, indexed parallel iterator into parallel iterator. Step skip. So here par iter. It always returns. Gosh. Where are the functions? Join scope. Okay, this is like fork join model. I can do spawn. Guide. Flatten, interleave, inspect, fold, filter, enumerate, chain, map, panic, position, repeat, take, try, update, well, sum. Okay, I think it will be easier to just do it on our own, I think. Actually, we can also start with non-parallel version, I guess, because we can just try to see if it will run fast enough. If not, we can try to speed it up a bit. So, oh shit, I deleted the code that I will need to write again now, which is a bit annoying, but okay. So, what do we do? So for each of our machine program, iter, let's do iter enumerate. So we have indices the positions of the instructions, and then we can filter them. And actually, oh yeah, we can just do early return, right? So once we find it, so we say enumerate. This will be index, and it will be in machine and instruction, and then this will be instruction with operation and with argument, and then match operation. If it is jump, nope, then we switch them. So yeah, I can just move it here, I guess. Here we can copy our machine, right? New machine, and then in new machine, which will also of course be mutable, in new machine we can take program, take index, and instead of that set it to instruction jump, and argument will be the argument we have. Then we will need to run it, but first let's do this. And if it's jump, then that will be nope. And if it's something else, then we just do nothing. And by default we return none, but then yeah, of course we need to dereference. Now with that machine we now need to check after the last instruction. Normally okay, that actually was also a mistake to already refactor that. Let's just say we can say run until repetition, right? And then we can just extract yeah. So we have advance is terminated, we have run until repetition. Here it accepts mutable self. Self. So now if I run my tests, they should still work. Okay, they still work. And now here's the only things that I need to do. I need to say new machine, run till repetition. And then if new machine is terminated, actually, is terminated sounds awful. Terminated is better. Terminated, then we just return, right? Some new machine accumulator. And if it is, okay, this is quite ugly, but doesn't really matter after the program terminates. So that's the same exact code, but let's first see if we can get it working. So this is our part 2, and we can now try to see if it works on the sample input first, because it will be also way faster. So part 2 solved. So I don't know. What should we get? We should get, by changing exactly jump, if you change the seconds, the program terminates. The program terminates, but then runs the instruction below. Constants the value 8. Okay, so in this case here, answer should be 8. Ooh, the index out of bounds. But the index is 9. And that happens in... advance. Yeah, if self-terminated. So we should only do that. We only advance if we have not terminated yet, because if we terminated, then we cannot advance anymore. Let's try it again. That was part. Is it? Oh, okay, so it works, I guess. Let's see if we can also see it working in interpreter. So day 8, part 2, sample 8, sum 8. Okay, can we run it on the input then? Oh wow, okay, no no parallel stuff was required. Okay, 1260, is it correct? Oh well, okay, that was a bit easier than I expected. Fine, we solved it. Okay, that was way funnier. That was, I guess, the puzzle that I enjoyed the most so far. And we can also make sure that we have a test for that. And the test runs, and all our tests run. So that ends this stream. Thank you for watching. I think that was so far the most exciting day 8. I really love the task. I really love modeling stuff like that. Really like to play with virtual machines, termination, programs. And yeah, I'm looking forward to having more puzzles in the same topic. I would expect that this will happen in the upcoming days. So yeah, I will do another stream in 2 days at 8 p.m. Central European Time, as usual, for days 9 and 10. So if you enjoy some Rust live coding, don't forget to join and don't forget to subscribe and like, and I will see you next time.